116 in your book, and it's kind of one of the most nitpicky pages of the chapter. Like the other one's over here, Ralph. I was like, you don't want to lose just one of the earbuds.
I saw it when I was just like, how did they bounce out like that?
Oh, because they're chaos personified. All right. So what we're looking at here is we're looking at 4 different equations that are all trying to tell us things. All right, my turn. You guys will have chit-chat time in a minute. Okay? So what this is was somebody got assigned a group project. We got 4 physicists, or actually more likely chemists. We're working with a radioactive substance. And they were writing an equation about how much is going to be left after some number of years. And I want you guys to see if they did it right. Are these equations the same? So I want you to try and look at this. We're going to think about it more in terms of like exponent rules and exponent laws back from like Algebra 1 days. And I'll write some of those up on the board while you guys are working. But I want you to look at page 127 has a lot of open space. I want you to see if you can figure out how these tie together. And I would recommend focusing on anything except the one with the 1/2. Okay? So use these 3 equations and see if we can figure out what they did to make them match. So I'm going to put some things up here on the board that may or may not be helpful. I honestly don't remember. So I'm going to just clear this part up. So you guys have like the whole space to work. We're going to write like 4 sentences at the bottom. Or actually, no, 3 sentence fragments at the bottom of the page. That's all we're going to write for part B. So you can use all that space. So I'm gonna write some of the old exponent laws up here. If we have times b to the x, that's the same thing, or b to the y. Nope. Sorry, that's got to be the same base. Oh, pulling these up out of my brain is being annoying. The x plus y. And if we have x to the y. And then also so that remember E is a button on the calculator. If you hit second and ln, it'll give you that E. Okay, I think these would be the only exponent laws we would use. Where if we multiply the bases, we're adding the exponents. And if we're multiplying, or if we're raising a power to a power, we're multiplying the exponents. So I'm going to name these just so it's going to be easier for us to talk about in a minute. But I want you guys to try. See what we can do and play around with these 4 equations and see if we can make one of them match another one. So I want you guys to try. Play with them a little bit. See what we can do.
Totally meant to do that. I am coordinated. Definitely not an accent from me.
We're gonna start talking about this in just a couple of minutes, guys. So I want you guys to try things. We are in about page 116. We're trying to see if we can get A, C, and D to match.
A, C, and D?
Yep.
Oh,
We're ignoring B for a hot minute because it's the most annoying.
alright.
And I put a couple of old exponent laws in algebra 1, but
Is that Ralphie Cooks? Ralphie Cookie Cooks? No, something like that. But that looked like it's fast enough. It's like it charges 32 million begins a second. You can't. This comes out. You hear me? Ralphie. Yeah, I just know you're not real full up way, bro. Bro, you really not putting some bills in on me. I don't. Bro, how you see my hands is grabbing, nothing's changed between me and you. Yours just look like you put your hands inside it's a movie theater popcorn. Like some church's chicken.
All right. So I'm going to start talking through some of this. And mostly I'm going to focus on equation A and playing around with that one to start with. And I'm going to change the view. So I labeled them just because the book doesn't label them and it makes it so much harder to talk about them if they're not labeled. And I'm going to erase this little decorative hill so I can use all this space. Because what we're trying to do is we're trying to use the exponent laws to see if they did, in fact, simplify and solve these equations the right way. So if I take that equation A, that Q equals 300 e to that gross decimal minus 0.0577 times t. And what we're going to do is we're going to use the exponent law that involved the two exponents being multiplied. So if x and y are multiplied, that means I can split them up and make them powers. So since this decimal and the t are being multiplied, I can split this up and make it so that I can get rid of the e. I can make this 300 times e to the gross decimal, 0.0577, and raise that to the t power to get the t by itself. And we might look at this and go, why? This is all stuff we can put in the calculator. E is a button on the calculator. So if I put that in the calculator and we do our 300 times, and I just simplify this piece. This is still equaling Q. I'm just going to put that down here. Equals Q. So I'm going to go into my calculator. And I just want to do the what's inside. So we're going to put E. And I tried to write it up on the screen and it was really small. If I hit the green button, that second button, and then I hit the LN that's 2 behind it, it gives me an E. And I can type in that decimal, the negative 0.0, can't read it, 577. And I can type this piece in as a decimal. And what we get is 0.9439. And oh wait, isn't that familiar? If we have this 0.9439 to the t. So what that did, if we used this exponent law, it took equation A, whoa, that was not what I meant. It took equation A and turned it in to equation C. That's exactly what this says. So we know for sure equation A and equation C absolutely match. We can do a very similar thing with equation D, except instead of it being adding my two exponents together, it's subtracting. So we can look at equation D and do the very same thing. I'm going to take, I need another color that's a little bit different. Let's go, we'll do it here. I'll do D. And I'm going to take all this gross decimaliness, 252.290 times 0.9439 to the t minus 3. So that's our original equation. And what I'm going to do, so I can give myself more space, is I'm going to split these apart. So we can do this as 252.290 times 0.9439 to the t times 0.9439 to the minus 3. That's what this says. If I'm multiplying the bases, it means we add the exponents. So as long as I multiply these together, we can absolutely do that. So it's pulling up the old exponent laws. They just picked the cruelest possible equation to try and get us to remember the old exponent laws. I don't know why they made us do it with decimals. If it was to the 3, that would have been a lot better than these gross decimals. But that's all they're trying to do is get us to remember these old exponent laws. They just tried to make it, I don't know, relevant, I guess. They're just jerks. And again, we can simplify this. I can take and type this piece into the calculator. My 0.9439 to the power of minus 3. And we get 1.1891 blah, 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 blah. So this piece over here equals 1.1891. Everything else is still the same. But since all these pieces are being multiplied, I can actually take my two numbers and multiply them together. I don't have to have them on opposite sides. So if I take my 252.29, because that's what's in the equation, times the 1.1891, we get what is essentially and roundably 300. So these two pieces multiplied together get us back to 300 times our 0.9439 to the t. So we made equation D also match equation C. So now we know that A and C and D all mean the same thing. And we can do B a very similar way. It's just significantly more annoying because of the fractiony stuff there. Yep. You mean on what? This guy? Got you. That is why I use colors, is it makes that communication so much easier. Oh my gosh. So we're using the old exponent laws that we learned in Algebra 1, we used in Algebra 2, and have promptly forgotten because, ew. That's what they're trying to get us to remember, is the old exponent laws. Yes, dear?
So did the t turn into the 0.9439?
So the t's still up here. We still have it. It was this guy, the minus 3, turned into the 1.18.
Oh, that was to the third that was turned.
Yeah. So they could have picked a significantly nicer way to get us to remember exponent laws, but I don't get to write the curriculum. We just get it. Okay, and the way we did from A to C is very similar to how we could do B. I could come in here and I could make this be 300 to the 1/2, and I could write out this as T times 1/12, and then do it the exact same way we did this one where we split it apart into two different pieces and put one of them into the calculator. It's gonna give us the same thing, but it's the exact same process as here. So they did do their project right. These four, I don't know why the physicists are dealing with radioactive products. It should be the chemists. Physicists don't do radioactivity all that much as far as I'm aware. They do stuff falling. But whatever, maybe the radioactive material's falling down some ramp. They usually deal with like how stuff moves. Pulleys and levers and ramps. Chemistry. This is chemistry. Okay, so this is a vaguely real situation, but it's not one that we're gonna real. So the other thing that they wanted us to do was they wanted us to look at these 4 different equations and figure out why they wrote 4 different equations. Filter. That came out loud. Yeah, give me a second. So what we're going to do is I'm switching this off of here. And we're going to look, this is part B, and this is the end of what we're doing today. We're going to look and we're going to see what each of these pieces is trying to get us to see and trying to get us to notice. Because there are reasons for each of these kinds of equations, and not just because they like to hurt themselves. They're just trying to see what's going on. And we're going to go through those in just a second. I'm turning around. So, what is something that is common in 3 of these equations? What do we see that's the same? What do we see that's the same in 3 of these equations? The 300. What is that 300 based on what we know of exponential equations? The starting amount. They started with 300 whatever units. They don't even, oh, it does say grams. 300 is the starting amount.
Did we write this in B?
Yeah, this is the part B stuff. So our initial amount, our starting amount, this one, and this one all tell us that. What else do we see? The 0.4 or 0.9439. We've got that in a couple of them. What is that? Do you remember what that's called? It's not the rate, but it's close. Because the rate, it'd be our percent change. It's a lot smaller. The 0.9439. Ugh. That's our growth factor. That's our base, the thing that's being raised to the power. What is our rate? What would be the percent of change? How would we figure it out? That would tell us our growth factor as a percent. So I'm going to write our original equation up here. This is our A equals P times 1 plus or minus R to the T. How do I find my R, my rate? Jadiana might have to stop playing the game.
Oh, is it the 1 minus?
Yes! Yes! Because we know that this piece is the same as this piece. So to find our rate, we're going to figure out 1 minus what equals the 0.9439. what is that rate? I want you to find it. What is that rate? 0.0561 or 5.61%. So that's not actually up here. It's kind of sort of based here. That's where they got that from, but the E likes to play weird games with that. So we've got all of the information from this guy. This person, they started with a different amount. And then they also played weird games with their time. So what person D was, is they missed the day of school where they started their experiment. So they came late. So their stuff had already started to decay when they had their first data collection. So they had to adjust for that. So they started with a different amount. I'm not going to do that in blue. I don't want us to think that's tied to that. So this one has a different starting amount. So they played with the time. So it caused a time adjustment. So that's why they did that weird unit of time there.
So what were we writing?
It's like this is the most important things we need right now. We're going to have one more piece, and I'm going to put at the bottom talking about B, but I'm just talking about Y. Oh, of course, no, my screen has decided it's going to freeze because I am not holding the laser pointer right now. We love this. It's so much fun. It's been doing this all day. You usually get once a period. I'll get a good freeze like this, and it'll come back. It just thinks it's lost internet. It hasn't, but it thinks it's lost internet. So we're going to talk about B mostly, that second equation that has the 1/2. Because this is a special thing, mostly in particular to chemistry. This is talking about something called the half-life. And what the half-life shows us is how long until it's cut in half. So it's going to take, oh, there we go, it's back. We're going to look at this piece here, and it's going to take, it takes, how many T's will we need in order for it to be cut in half one time? So, oh, that was not an eraser. What does T need to be? I'm going to write that piece again. I'm just writing things down. Ah, there we go. Back. If we have 1/2 to the power of T divided by 12. What does T need to be for us to wind up multiplying 300 by 1/2? What would that exponent need to simplify down to be? I feel like I'm wording this badly. 6 would give us an exponent of 1/2, but I don't want to raise this to 1/2. I want this to just be 1/2. So we would need this exponent to be 1. So what would T need to be for this exponent to be 1? 12. So it takes 12 T's for it to have. Which I feel like that spells wrong. Cut in half. So when it has a base of 1/2, they're trying to show the half-life, which is a very chemistry, radioactivity specific concept. We're not gonna work a ton with Half-Life. Half-Life likes to play with our units of T a lot. And that was what they wanted us to see out of B. That the half-life means it takes 12 years for it to cut in half. It decays by 5.61% per year. We've got a 300 starting amount. Part D is just that guy was late. So he did weird things with his equation, trying to make them match up. So the most important things for us to figure out from here, from looking at these equations, is that starting amount didn't change for the people who were there on time. So the starting amount is consistent here. And they all have the same rate of change. They're just showing it to us in different ways. The E is so you can calculate it continuously. That's from, you remember back to when you did Algebra 2, continuously compounded interest stuff, bank account stuff. We'll get into that later. That's what the first one is I could figure out exactly how much is there every single day. The third one, I could figure it out as years go. It's going to be the same thing, but it's only calculating on the year. Okay, so again, we're not going to do a ton of work with chemistry. We're not going to do a ton of work with weird stuff like that. In fact, I think we only have one more day when it's not money. Okay, so I wish they had done this with less decimally things, but really what they were trying to get us to notice on these was that we can still use our exponent laws and that all those pieces are still there even when it's decimally and gross. Okay? There's not an additional homework today. Happy Thursday. We're almost to Friday. Today officially starts the alphabet countdown in elementary school, if you remember doing that. ABC countdown started today. So we have 25 more school days because today's done. So 25 more school days.